Okay, we got a little review here for lenses and mirrors. I'm going to go through all the ray tracings. You can just kind of match up what you have. I'll try to be descriptive when I do each one. There'll be 6 total, and you can kind of scroll along to whichever one you want a little bit of help with. So if I had to describe this one, I would say the object is in front of the focal, so the focal is greater than DO, and this is a concave mirror. That's how I would describe this particular one. So we use our rules. It is a mirror, so it's going to bounce off or reflect, and it's going to bounce off based on the focal. Come in parallel, leave based on the focal. Our second ray rule tells us to line it up with the focal and then bounce off parallel, so they're exact opposites of each other. The third ray rule, come in, origin, then leave at an equal angle. I'm just going to guess what that angle would be. That looks about right. I might be sorry I did that later. You'll have graph paper, so it'll work better for you. And then you want to do a trace back of the reflected rays, and where those rays intersect, yep, knew I'd be sorry, is where the image forms. So my image is over here. So if we had to describe this, we would describe it as virtual as it forms on the negative side of the mirror, erect as the arrow is pointing up, and I'd also say that it was enlarged. So the question is, what's the real life use for this? Shaving mirror, makeup mirror, compact, whatever you want to say, but that would be a real life example for this. So that's the first one. Let's go to the next mirror, which is also concave. In this example, DO is greater than the focal. This is an example of a concave. So what you do is you take your arrays and go through the same process. It's so weird talking to myself here. Go in parallel, leave based on the focal. For ray 2, come in based on the focal and leave parallel. Ray 3, go in through the origin, leave at an equal angle. Where these intersect is where the image is formed, so we'll label it I for image. We can describe this one as well. I would describe it as real as it's projectable or forming on the positive side. It's inverted, and it is, in this case, enlarged. However, if I continue this DO, if DO gets greater than 2 times the focal, it would then become reduced. But in this situation, it's enlarged. And what could we use this for? This would be a great thing as a reflecting telescope. That would be a real life example for this. The last mirror is convex. I'm not even going to compare the distance for the convex mirror. Want to come in parallel. This time we're going to move away. So this should be over here. That's a mistake. The focal should be over there, as it is virtual. And you want to move away from the X. And then we're going to try to get to the focal, and we're not going to make it. So we're going to leave parallel. And the last one is we go to the origin, the only flat part of the mirror, and leave at an equal angle. And you can see that it's going to be virtual, as they're all going to form over here. So we trace them back, and where those rays intersect is the location of the image. So the image would be there. Can't even see my arrow. The image is there. It is virtual as it's on the negative side of the mirror. It is upright, it's erect, and it is reduced. So virtual, erect, reduced. What's an example of this? This would be a security mirror. Never flips upside down. Can't get across the focal. Can't project it, but you can see around corners with it, so it's security mirror. So I think I'll stop and I'll make another one for lenses.